Now we are recording. All right. So we are trying to solve this equation. I'm just repeating it for the sake of recording. So we try to solve this equation for a beam. We guess an answer, yxt. Let's put it inside a box, not that box. So we guess an answer, we did the derivative, we ended up with the second equation, which is an ODE. We guess a solution for that one, and we ended up with 4 solutions for yx. So as with all ODE, we know that a combination of these can be a solution. Typically, we don't like to work with complex number, like e to the power of ix, something that it makes us uncomfortable. What we will do, we try to use the Euler formula and substitute it. So what I can do then, I can, for example, write down that e to the power of, let's say, lambda x plus e to the power of minus lambda x divided by 2 give me cosine hyperbolic of lambda x, and e to the power of I lambda x plus e to the power of, this is I, minus I lambda x divided by 2 give me cosine x, and similarly e to the power of lambda x, e to the power of minus lambda x divided by 2 give me sine hyperbolic of x, and e to the power of now I lambda x minus I lambda x give me sine x. All right. So if I combine all of that, and as I said, a linear combination of them or any linear combination, my yx will be a cosine hyperbolic of lambda x, b sine hyperbolic of lambda x, b cosine x or lambda x, plus c sine lambda x. So, and here is the solution for that 4th order differential equation in the box that we have. Okay, so let's number them, and rather than that box, we can just call the equation 1 and 2. So here is the solution for equation 2. I always thought this sine and cosine hyperbolic, what they can be used for, but here is one example. Yes.
For that,
right. Oh yeah, this is positive. Yeah? Thanks. And if you forget the sine and cosine hyperbolic, you better quickly check them. Right? So they have a different shape. Just to remind yourself of what was the shape of sine and cosine hyperbolic. I know we neglect them, so we pay a lot of attention to sine and cosine, but not the hyperbolic one. All right, so here is one use of them. So we get to this solution for yx, and we know this yx is the mode shape, right? And now, what I need to do is figuring out these A, B, C, and D. And similar to a string, what we need is the boundary conditions. We need B, C's. And we need 4 of them because we have 4 on now. So now let's get to a particular example. So far, it was for like a general beam. So as an example, let's consider a cantilever beam. But in future, you may be asked to do for a different beam. If you know how to do it for this beam, then it can be applied to any other beam. So a cantilever beam, we'd better draw one. So we figure out what are the boundary conditions. So if I have a cantilever beam, let's say whatever motion it does, for example, if it deflects. So what I can say at this point, at x equal to 0, it's obvious that yx or y must be 0, and also derivative of y with respect to x must be 0. This is the slope, right? And this is the displacement. So that's two boundary conditions. I need two more. As the name implies, I need boundaries. So I'll rely on the other end. So what's going on the other end? So I don't know anything about the displacement or the slope, because at the other end, the slope is something that we don't know. And the deflection is something also that we don't know, right? So maybe we need something else. At this point, we need to rely on maybe force and moment. I know at the free end, so this is a free end. So let's look at that. This is a free end. And at the free end, there is no M, and there is no shear force. Do you agree? It's free, it's just air. There is nothing there. So how can I use these M and V? We go one step back to the equation that we had. Let's go when we develop the equations. We have the M and V somewhere here. Let's try to find them. Okay, it's here. So this is my equation for M. Take a look at this one. M, the one that I'm highlighting, is EI, derivative of y with x squared. And here is my V. So these two things must be 0. Do you agree? So let's go back and work through them. So M is equal to 0. Therefore, EI, derivative of second derivative of y with respect to x squared, which is equal to M, or we said minus M, must be equal to 0. From here, I have d2y divided by dx squared. But at which point? When x is equal to L. At x equal to L is equal to 0. So now we got, so far, 3 boundary conditions. At x equal to 0, y is 0, the slope is 0. At x equal to L, the other end of the beam, derivative of y with respect to x2 is 0. And v, we know v is always is derivative of M. with respect to x, we had it above, and it has to be equal to 0. So it gives me the third derivative of y with respect to x3 at x equal to L must be 0. And here we are. We have 4 boundary conditions, so we can find A, B, C, and D. Right? Let's pause here and see if you have any question or if you like me to go over again. But always have the big picture in mind. So we have a beam, all right? We get to an equation of motion. We try to solve it. And what we did, we guess a solution, and we managed to find yx, one part of the solution, the part that it's independent of time, right? So there is no time here. Remember, let's go back here. We separate solution. We said maybe this yxt, I can separate x and time as just one solution because it's easier to deal with. We substitute that things there, and now we are attempting to solve yx. We got to that one. As an example, for any other example, it is different. The boundary conditions are different. So we are focusing only now on a cantilever beam. For a cantilever beam, two end, x0, and this end, x equal to L. Each side, we have 2 boundary conditions. So the rest is just some messy math, taking the derivatives 2 times, 3 times, and substituting these zeros. Some of them become 0. Let's skip all those math. I leave it to you because it's really boring. So some math. We will find, I did the math before, cosine lambda L multiplied by cosine hyperbolic of lambda L equal to -1. You can try it on your own. It's easy. It's just a lot of pain. Taking the derivative, substituting this value, simplify these things. After some math, you will get to this equation. So I know L, and I'm looking after finding this lambda. So I need to solve this equation, but it does not look like a simple equation to solve it. I try to solve it, but it's not possible. So when we cannot solve an equation, we need to rely on numerical method, right? Which is this case, or just trial and error by putting different values for lambda and see if you can find something that if I multiply cosine of that something by cosine hyperbolic of that things give me -1. Or a better way, rather than just randomly trying it, is just to plot just one solution again. You can put it inside the loop to find the solution, but one smart solution is to say, if I have cosine lambda L equal to -1 divided by cosine hyperbolic lambda L. So if I plot these two graphs, so cosine, let's say, and 1 over cosine hyperbolic of lambda L multiplied by a negative sign, maybe give me something like that. Just randomly plot something. So whenever these two intersect, it's my solution, right? This is one solution, this is another solution, and so on. That's another way when you see an equation which you cannot solve it, like this one. you can use the numerical method or just simply plot it for different value of lambda L and see where it goes. This is for that one, and this is for this function, and the intersection of them, which I can bring it here. I plot them in MATLAB. Can I? Okay, let's see. All right, so here is my graph. And you can see, right? The red one is the cosine x, and the blue one, 1 over cosine hyperbolic of x, bless you. So here is one solution, which I measured, yes. Here is the second solution, and the third solution. Of course, we can continue for whatever we want, because it has infinite number of solutions. So in MATLAB, I could zoom and find the exact values, which I did, and it gives me those solutions. Lambda L, solution number 1, is equal to 1.875. I went for 3 digits after the decimal point, but you can go for more accurate. Lambda L2 is 695, and lambda L3 is 7855. We have lambda L infinity. Infinite number of solutions for this problem, because the cosine go forever, and the 1 over cosine hyperbolic also continues, so all get different values. Give you a moment to take notes. So now let's remind ourselves what was lambda. If you recall, to simplify our life, we substitute something with lambda. So lambda was m omega squared divided by EI. Things that has meaning for us. So from here, then I can find omega, which is lambda 2 the square root of EI divided by m. EI divided by. All right. So I have the value for lambda L, 1, 2, 3, 4, and so on. So it means I have several natural frequencies. So my omega 1 then will be 1.875 squared EI ML4. I just take L inside the square, so make it a little bit neat. Omega 2 will be 4.695 EI ML4. Omega 3 will be 7.855 EI ML4, and so on. Here are the natural frequency of this system. We have all these values. We know the material, all right? So it depends on if this beam is aluminum, copper, steel, we get a different natural frequency. So that's E. I is the cross-section moment of inertia. So we are not limited for a square cross section. This beam can have any cross section. So beam cross section can be anything. Like it can be a square, and I know how to find I for a square, right? Which is 1/12 EH3. It can be a circle. Which you know how to calculate pi for a circle. It is pi/64 d4. Or it can be like a pipe, maybe a thin wall pipe. A circle somewhere. Ooh, there it is. Okay, so which vibration of pipe also is important? Important things, which I will discuss it shortly. All right, so if you happen to analyze a pipe, which let's say has the thickness T and the average radius R, then I for these things is equal to IR3T. So the I, the second moment of inertia. So it depends on the geometry of the beam, the material property. So this value can be different. The modulus of elasticity, I, M, and of course the length of the beam. So that's a constant. So if I know that constant and we solve the lambda before, so as you can see, we managed to find the natural frequency for this system. So, but let's get back to the idea that we were trying to solve. We were trying to solve these yx, which had a, b, c, d. We substitute the boundary condition. This is one equation that we ended up with. After we managed to find lambda L, we can solve the rest of equations. As I said, it's a lot of work, but boring, nothing very interesting. So you will get to your yx, which is equal to, so I did the hard work today, and you just need to write it down. Because I thought if I do it in the class, it's gonna, all of you are gonna go to sleep. There is no value in doing that, a lot of derivatives. So it is sine hyperbolic of lambda L plus sine lambda L divided by cosine hyperbolic of lambda L and cosine lambda L multiplied by cosine hyperbolic of lambda x minus cosine lambda x plus sine hyperbolic of lambda x and sine lambda x. So here is our yx. But wait, we know this lambda, we don't have just one answer for them. We have n of these things. So it means I have n y and x, similar to a string. So each of these things, I have to put an n there. Lambda n, which we managed to find them. We know the value for lambda 1, lambda 2, and so on, right? They are all in previous slide. And this is what we refer them, as we discussed before, as the mode shapes. So if I have a beam, a cantilever beam, this beam naturally can have one of these shapes, y1, y2, y3, and so on. And they are independent of the time. They are just the shape, right? The geometry depends only on the lambda, which is a constant value, and x, the position, okay? So if I plot these things, so let's plot a few of them. So here is my beam, and let's say 1, 2, and this one is 3. 3 is on. So here is a beam that I have. This beam, if I, let's say, excite this beam, so it can have any motion. Let's say it can have this motion, or any other random motion, but something reasonable, obviously. And here are the modes. This is my y1x. Omega 1, which we calculate omega 1 above. It is whatever, just not going to write. This is my omega 2. Of course, I use MATLAB. I didn't guess the shape of these, right? No one can guess what this looks like. But you can easily plot these things because you have the value for omega 1, omega 2, or lambda. Just calculate them. And this guy will be and so on. So this is y3x and omega 3. So omega 1, let me write it down again. 875 squared and 4. This one was 4695. 7855. And so on, up to infinity. Right? Again, as I emphasized before, the math around these things, you can figure them out. It's just some, they are simple but long. It's important to understand what actually we are doing, right? So we said if you have a cantilever beam, if you excite it, it can have any shape, a reasonable shape like this green one. But we can break it down similar to the string to different shape, which we call them mode shapes. And each of these mode can move with the frequency, like it can move with the first frequency and with the shape that, as you can see, of course, it has to follow the geometry. For example, at the beginning, the slope must be 0. Right? And we can have several of these. Now, what is my actual response? Or that green is sum of all these responses. Right? So this is what we were looking to find. This is a function of x and time. All right. And we just proved that this function of time and x can be written as yx. We choose sine or cosine. I forgot it was sine or cosine. Doesn't matter, but where, okay, here it was our initial guess, right? Yx and t is yx sine omega t. You can go with cosine, doesn't matter. So sine omega t, but sum of all this stuff, so it is sum of n equal to 0 to infinity for yn x and omega n. The more n I include, the more accurate result I will get. But similar to a string, as we discussed before, usually the first 4 or 5 modes gives us an accurate result. Most of like analysis, people, this is what people use. You may ask, okay, who cares about the vibration of a cantilever beam? In fact, there are many, many applications just for the vibration of a cantilever beam. Just consider a propeller, which roughly, let's say it has a shape of like this shape. Very ugly propeller, but you got the idea, right? And it is actually each of them acts as more like a cantilever beam, and we need to be careful at some speed. If you are getting close to their natural frequency, then the whole things will break. Or in a car, the same. When we put a motor on a, let's say a subframe, the subframe usually is in a form of a, not a cantilever beam, but a fixed beam. So, and we have to be careful, the vibration of this system, the natural vibration of this system is not close to the excitation vibration. So it has application. And the math is long and ugly, but it is very useful. So with the time that left, I'm just going to quickly, in 3 minutes, show you like these mode shapes and see if it is matched with what we have in finite element. You can do these things in like SolidWorks. SolidWorks, I'm not quite, yeah, SolidWorks. Or in Adams, this is Fusion 360. Let's say I quickly create a beam. So let's say I have a beam like this one, and I go for material steel for now. Then I need to make a cantilever beam out of it. So I'll go to simulation. So most of software has some sort of simulation for what we want. Fusion has like modal analysis. So if I want a cantilever beam, I need to fix one side. Okay. So now I have a cantilever beam, I fix one side. Let's say we stay with the material and we solve it. So it takes maybe 30 seconds for the system to solve it. Okay, solved. All right, here is our cantilever. All right, this is my first mode. And the software give me its natural frequency. It is 1.39 hertz, depends on the material, the cross section. And if I look at it is important, guys, please stay with me in class for 2 more minutes. So you have an easier time following those math. So this is let me make it two-way. So this is the first mode. Of course, it's a slow motion, and that's the shape of the first mode and the natural frequency that the software is giving me. Now let's go to the second mode. Here is the second mode, and you saw we get to the same one. And here is the motion, obviously. So with software, we can find the mode shapes and the natural frequencies. Now, if I excite, let's say, the base of these things with something, I can find the solution of that. Obviously, software can do it for me easily, but let's say if I want to do it, and let's say going for very, very high, like mode, maybe something more interesting, 8. So that's more 8, mode 8. And as you can see, it has that shape. All right, so one last thing that I want you to pay attention is like this point, which we call them node or not. And I want you to pay attention how many nodes we have for each of them. Like the first one, we have 0. The second one, we have 1 node. The third one, we have 2. So for each n node, we have n mode n, we have n minus 1. And why they are important, those points? Because the beam does not vibrate at those points. So let's say in mode 3, this point has no vibration, right? Does not move. Let's say if I want to put a sensor somewhere on this beam and I want minimum amount of vibration for that, maybe that's the best place to put it there. If I know that my excitation is around omega-3, right? So please review this one. On Monday, we will get to more interesting topic, which is we want to see what is the vibration of a plate. Like right now it's 2D, now we're going to get to 3D. And always 3D is more fun, right? Like 3D movies. Thank you, guys. If you have any question, I'm staying outside. Hello. How are you?
Good, how are you?
Not bad. Let's go outside.
Just want to understand that what's happening a little bit better.
Right.
So we have these n different bond shapes,
Right.
and we have these n different natural frequencies.
That's right.
And then you talked about exciting it at a certain natural frequency.
Right.
So say we take the beam and we excite it at natural frequency omega 3.
Right.
We're going to expect the oscillations to be of the
Shape.
shape Y3.
That's right.
Okay.
We are going to expect to see an oscillation, which is very close to the mode number 3.
Right.
It doesn't mean that it doesn't have other stuff, but it's going to be dominated by that one.
Okay.
Right? If I excite it by something that
Does it matter where you excite it? Like what if you put the force here versus here versus in the middle?
No, it doesn't matter. That's why in grad school you would see, even we have a course here, no, that you take a hammer, you excite it at some point, or you put a vibrator at some point. But for bridges, they do that. They
Okay.
do it at one point,
Yeah.
and they have to travel through the whole.
Right. Okay. And if you excite it at a random frequency,
Oh, let me stop. I forgot to stop recording.